Welcome to session 1, chapter Gravitation. From our school days, we have been learning what is gravitation, right? So what is gravitation? Gravitation is a natural phenomenon by which material object attracts one another. So this is what we call as gravitation, right? So when two bodies attract each other, or suppose I throw a ball down, the ball gets attracted towards the earth, we are calling it because of a natural phenomenon called as gravitation, right? Now, in this chapter, we are going to learn an important law of gravitation, which is called as the Universal Law of Gravitation. Now, why is it called as Universal Law of Gravitation, Universal Law of Gravitation, and what is its statement? Before learning that, let us see the small history about Universal Law of Gravitation. Sir Isaac Newton was the one who formulated this law. In 1665, when he was in school at Cambridge, Lincolnshire, he was forced to sit at home because of a pandemic which had arisen in Lincolnshire, due to which there was an indefinite period closure of colleges. Because of which, Sir Isaac Newton was forced to stay at home. And when he stayed at home, he got an opportunity to discover, to think, to analyze a lot of things at home. So he started thinking one by one about different aspects around him. So the most important thing, what was troubling him was a question, that is, what is a force that produces acceleration which is towards the center of the earth? So you all know about the Newton and the apple story. The story says that Newton was sitting under an apple tree and the apple fell down, and Newton started thinking like, why this apple fell down? So then he got this universal law of gravitation in his mind. That is what it is said. But that gave the answer for his question, that there is a force which is producing acceleration and which is being attracted towards the center of the earth. The apple was getting attracted towards the center of the earth. This is what he thought. Now, the second question what arose was, what is the law which is governing this force? There is some force which is attracting this apple down to the center of the earth. But what is that law which is governing this force? So when he started experimenting, when he started analyzing things going around him, he said that, he declared that the laws of nature are same for earthly and celestial bodies. That is, the bodies in the sky, in the universe. So he said that the force between the earth and apple is equal to force between the earth and the moon. Right? So therefore, this law was called as the universal law because it was being applied to not only earthly bodies but also celestial bodies. Right? Then he analyzed that the acceleration is inversely proportional to square of the distance. So as the distance went on increasing, the acceleration went on decreasing. Then he also stated that, yes, now since force is equal to mass into acceleration, therefore force is directly proportional to the mass of the body, right? And the force is also directly proportional to the mass of the earth. Now, why he said that not only the object but the force is directly proportional to the mass of the earth was because when an object was being attracted towards the center of the earth, there was an equal and opposite force given by the earth towards the object. So therefore, we could say that the force which is acting on the mass of the body is equal to the force acting by the earth, mass of the earth. So therefore, he said that the force is directly proportional to the mass of the body, the force is directly proportional to the mass of the earth. So when we combine these three things, we get that force is directly proportional to the mass of the earth, mass of the body, and inversely proportional to square of the distance between them, right? So if we remove this proportionality sign, we get a constant called the gravitational constant, G. So F is equals to G capital M, M upon R square. Now this gravitational constant value was not determined by Sir Isaac Newton because he didn't get to know what is the actual value of gravitational constant. We will discuss about that in the later part. But after a few years, the value of gravitational constant was determined to be 6.67 into 10 raised to 11 Newton meter square per kg square. So this was the value of the gravitational constant. And this equation, that is F is equals to G into M upon R square, was called the Universal Law of Gravitation. Now, not necessarily every time we take capital M as the mass of the earth, we can take, when we are talking about two different objects, we can take the masses as M1 and M2. So we can also write this expression as G into M1 M2 upon R square, where M1 is the mass of first object, M2 is the mass of the second object. So therefore, now let us state what is the universal law of gravitation. The universal law of gravitation states that the force of attraction between two particles or two objects is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Now, when we say this statement, we also have to keep a note that when we are saying F is directly proportional to the product of the masses, so that means as F increases, as the mass increases, the force also increases. So as the mass of the bodies increases, the gravitational force also increases. And since it is inversely proportional to the square of the distance between them, so as the objects start moving far away from each other, the gravitational force also starts decreasing. So closer the objects, more is the gravitational force. Farther the objects, less is the gravitational force. Alright? So now we mentioned what is gravitational law, universal law of gravitation, what is gravitational constant. We also told the value of gravitational constant. But as mentioned earlier, the value of gravitational constant was not determined by Sir Isaac Newton, but by a scientist called as Henry Cavendish. By a scientist called as Henry Cavendish, almost 76 years after Newton formulated the law of gravitation. In actual, he was trying to determine the density of the earth, and in this process, he determined the value of G. Now, to determine the value of G, he performed a small experiment called as the Cavendish Experiment. The setup of the experiment is like this. There were two small spheres and two big metal spheres. The two small spheres were attached on either side of the wooden rod whose length was L, and they were suspended by a quartz wire which is free to rotate. The two big metal spheres were kept in such a way that the distance of the bigger spheres from the small spheres were almost equal, right? And they were kept in such a way that they formed a concentric circle, right? Now, the gravitational force attracts these small spheres towards the larger spheres, and because of this, the smaller spheres started moving towards the larger spheres. Now, when these started moving, they moved across an arc of this circle which was of a radius which was equal to L by 2. Now this gravitational force of attraction was till when this was equal to the restoring torque. That is, the torque of gravitational force or the gravitational torque was equal to the restoring torque. Till then, the smaller spheres tried to move towards the larger spheres. Since the restoring torque is in opposite direction, we put a negative sign here. Now, what is gravitational torque equal to, or what is torque equal to? Torque is nothing but the force into perpendicular distance. Force into perpendicular distance. So F into L. So when we are talking about the gravitational torque, this is the gravitational force into the length of the rod. Now what is this gravitational force? This is equal to G into M1 M2 upon R square into L. So M1 and M2 are the masses of the spheres and R is the distance between the two spheres and L is the length of the rod. Now what about the restoring torque? The restoring torque is equal to K into theta, where K is restoring couple per unit twist and theta is the angle made by the restoring torque. Now, we have to equate these two equations. So when we equate these two equations, we get F into L is equals to K into theta. Negative sign just implies the direction of the torque. So G into M1 M2 upon R square into L is equals to K into theta, or I can say G is equals to K into theta into R square upon M1 M2 into L. Now knowing the values of the restoring couple per unit twist, the angle through which you rotate the fiber, the distance between the two spheres, the masses of the spheres and the length of the rod, Cavendish calculated the value of G to be 6.67 into 10 raised to minus 11 Newton meter square per kg square. Using this experiment, Henry Cavendish also tried to determine the mass and density of the earth. Now, he assumed that there is a body of mass m on the surface of the earth which is at a distance of RE, that is the radius of the earth, and the mass of the earth is concentrated at the center of the earth, which is equal to m into E. Now according to the Universal Law of Gravitation, F is equals to G into ME into M upon RE square. Now this force is equal to the weight of this body which is acting downwards. So this force is equal to mass into acceleration due to gravity. So we can say that since these two equations are similar, we can equate m into g is equals to g into me m upon re square. So we have m into g is equals to g into me into m upon re square. Now this m and this m gets cancelled. Now we know the value of acceleration due to gravity, the value of radius of the earth and the value of gravitational constant. So through this we can calculate the value of mass of the earth. So what are the values? G is equals to 9.8 meter per second square. Capital G is 6.67 into 10 raised to 11 Newton meter square per kg square. Radius of the earth is equals to 6 into 10 raised to 8 meters. Okay, and yes, so now we can calculate the mass of the earth. So what is mass of the earth equal to? So I take this radius of the earth on this side. So we have g into re square upon the capital G comes down. So we have capital G here. So we get 9.8 into 6.67 into 10 raised to minus 11 into 6 into 10 raised to 8 divided by, this is going to be 6 into 10 raised to 8 divided by 6.67 into 10 raised to minus 11. So when we calculate this, we get the value of the mass of the earth to be 6 into 10 raised to 24 kg. 6 into 10 raised to 24 kg. So this is the mass of the earth. Now what about the density of the earth? So density of the earth is given by rho e. The symbol of density is rho. So rho e is equal to mass of the earth divided by volume of the earth. Now volume of the earth, since we consider the earth is spherical in shape, we write the volume of the earth to be 4 by 3 pi re cube, where re is the radius of the earth. So when we try to put the values here, mass of the earth is 6 into 10 raised to 24 divided by 4. This 3 goes up, so it is into 3. 4 into pi value is 3.142 into radius of earth is 6 into 10 raised to 8 the whole cube. So if you calculate, you get it approximately equal to 5.5 into 10 raised to 3 kg per cubic meter. And this is the value of density of earth. So this is how Cavendish determined the value of gravitational constant. He determined the value of mass of the earth. He also determined the value of density of earth. This is all for today. Thank you.